Assalamu alaikum everyone and welcome to lecture number 17. In this lecture we will talk about the continuous time Fourier transform, and while talking about this we will answer very important questions regarding the aperiodic signals. So let's get started. So we are starting the chapter number 4 of this textbook. In chapter number 3 we learned about the Fourier series and we learned about how it can be used to represent the periodic signals. And not only the representation, the Fourier series was very useful in analysis of the periodic signals, synthesis of the periodic signals, and to find the response of LTI systems for periodic inputs. But the question arises here is, what about the aperiodic signals? So what I'm going to tell you is probably the Fourier's most important contribution. He thought of the aperiodic signals as periodic signals with infinite period. We'll see that with example just up. So, and with this thought process, we will develop the Fourier transform representation for aperiodic signals. So suppose we have a square wave defined something like this for one period. So the square wave is 1 for t mod less than t1 and it's 0 for t mod greater than t1 and less than t by 2. This is the same square wave used in example 3.5 and we found its Fourier series coefficients. So anyways, let's draw this square wave again and we can see that it is 1 from minus t1 to t1 and 0 otherwise in the time period. So this time period here we can represent it from minus t by 2 to t by 2. The Fourier series coefficients identified in the example 3.5 were something like this. It is 2 sine k omega naught t1 divided by k omega naught t, where the omega naught is a fundamental frequency defined as 2 pi by t. Now let us define an envelope function of tak, like t times the Fourier series coefficients. And while defining the envelope function, what we will do is we will replace these discrete k omega naughts with a continuous variable omega. So this figure here shows the Fourier series coefficients multiplied by t for various time periods. And the Fourier series coefficients multiplied by tak are represented here by these bars here at every k omega naught, and over top of these coefficients we have plotted the envelope function of the same tak. Now as we increase the time period from 4 times t1 to 8 times t1 and then to 16 times t1, we can see that the Fourier series coefficients are now much closer when the time period increases. So for the arbitrary large case of t, suppose we increase this time period to a larger value, we can conclude that the Fourier series components are spaced even closer. So what happens when this time period is approaching infinity? Then the set of Fourier series coefficients approaches this envelope function which we have shown in this figure. It will be something like a continuous function. So we can see a counterexample again and we can develop the Fourier transform representation for the periodic signals. So consider an arbitrary periodic signal x of t, which is a finite signal from minus t1 to t1 and it is defined 0 otherwise. And let us define a periodic version of x of t which is represented as x tilde, and essentially x tilde is x of t repeated at every time period t of our choice. So since the x tilde of t is a periodic signal, we can represent this signal in its Fourier series form as in the standard form summation k equals minus infinity to infinity a k exponential jk omega naught t, where the Fourier series coefficients can be found by the analysis equation, which is 1 over t integration over a time period which is minus t by 2 to t by 2 x tilde of t exponential of minus jk omega naught tt, where omega naught is 2 pi by t. Now since we know that in this interval from minus t by 2 to t by 2, x tilde of t is actually equal to the original signal x of t. So we can substitute this x tilde of t by x of t in the above integral. And since we know that the aperiodic signal x of t is 0 outside the interval minus t by 2 to t by 2, as we can see here, it is 0 outside the interval of minus t by 2 to t by 2, we can change the limits of integration from minus t by 2 to t by 2 to minus infinity towards infinity. And multiplying t on the both sides of this equation will yield tak equals integral of minus infinity to infinity x of t exponential of minus jk omega naught t. So let's define envelope of this tak, in which we will replace this discrete k omega naught with a continuous variable omega. So here it is. The envelope function of tak is defined as x of j omega integral x of t exponential of j omega t. Again, the omega is a continuous variable. Then the coefficients ak here can be represented in terms of the envelope function as 1 over t, the envelope function, and the input argument of this envelope function will be the discrete values of omega, which is k omega naught. So now we have the Fourier series coefficients of our product signal x tilde. We can represent this signal by Fourier series as this synthesis equation, in which we have summation of the Fourier series coefficients multiplied by the complex exponential having frequencies at k omega naught. Now, since we know that the fundamental frequency here is 2 pi by t, rearranging this one will yield 1 over t equals omega naught over 2 pi. So this 1 over t can be replaced by omega naught over 2 pi in the above summation here. The 2 pi is carried out of this summation and omega naught is left here inside the summation. Let's visualize this equation from this graph, and here we have plotted an envelope function of x jk omega naught e jk omega naught by replacing this k omega naught by a continuous variable omega. For ease of representation, I am defining x of jk omega naught e jk omega naught t as L jk omega naught. Therefore, at a particular value of k omega naught, we will have a sample here with a height of L jk omega naught, and the next sample in this summation will occur at k plus 1 omega naught. Again, it will have some height. We can observe from the figure that this height multiplied by the width is the area of this rectangle, which can be written as x of jk omega naught exponential of jk omega naught multiplied by omega naught, which is the term here in this summation. If the time period t of this product signal x tilde approaches infinity, then this omega naught or the fundamental frequency will approach 0, and therefore the spacing between k omega naught and k plus 1 omega naught will become infinitesimally small, and the area of all these rectangles will converge to the area of this continuous function or this envelope function. Therefore, the summation becomes the integration of the continuous envelope function, which is written here, and the variable of integration here will be d omega, which is this x-axis of the graph. Another point to notice here is, as t approaches infinity, the product signal x tilde approaches the aperiodic signal x of t, because the signal will never be able to repeat itself. Therefore, we can replace this periodic x tilde with the aperiodic x of t, and we can rewrite the same integral equation. X of t equals 1 over 2 pi integral x of j omega exponential of j omega t omega, where x of j omega was defined previously as integral of x of t exponential of minus j omega t dt. And these two equations are called the Fourier transform pair, in which the first equation is the synthesis equation and the second equation is the analysis equation. From these equations, we can observe that the aperiodic signal x of t can be represented in the form of complex exponentials. where the weight of these complex exponentials can be identified by the analysis equation. There are important points to observe here. The periodic signals were represented by complex exponentials having discrete frequencies, and these complex exponentials were related harmonically. On the other hand, the aperiodic signals can be represented by complex exponentials as well. However, the complex exponentials have the continuum of frequency. That means the omega here is a continuous variable and can be any value from -infinity to infinity. And these complex exponentials of different frequencies do not need to be harmonically related. And finally, x of j omega is the spectrum of x of t. Now let's compare the Fourier series coefficients and the Fourier transform of a signal. Suppose we have the same periodic signal defined above, which is x tilde, and it can be represented by its Fourier series with the coefficients ak. And the Fourier series coefficients can be identified by the analysis equation as 1 over t integration from -t/2 to t/2, the signal itself multiplied by exponential of -jk omega naught t dt. Since x of t equals x tilde of t, for this particular interval here, we can replace x tilde by x of t in this equation. And again, we know that this x of t is 0 outside this interval, so we can change the limits of integrals from -infinity to infinity. Previously, we have defined integral of x of t exponential of -j omega t dt as the Fourier transform of x of t, which is x of j omega. Therefore, the Fourier series coefficients become 1 over t x of j omega, where omega is equal to k omega naught. Therefore, the Fourier series coefficients of a periodic signal x tilde are proportional to its Fourier transform over one period. So let's summarize what we have learned so far in this topic. Firstly, the concept of Fourier series can be extended to develop the Fourier transform representation for aperiodic signals. And this was made possible by thinking of aperiodic signals as periodic signals with time period infinity. And after the development of Fourier transform representation, we can also see that the aperiodic signals represented by the complex exponentials. There is a major difference. The complex exponentials in the periodic signals were having discrete frequencies. However, the complex exponentials for the aperiodic signals are having continuous frequencies. In other words, for the aperiodic signals, we would have to add infinite number of complex exponentials to recreate the aperiodic signal. The contribution or the weight of each complex exponential is x of j omega, or the Fourier transform. Therefore, the Fourier transform of a signal gives the insight of frequency composition of the signal. For example, with the Fourier transform, we can know what frequency range is present in the signal, or what are the dominant frequencies. Is the signal mostly comprised of higher frequencies, or is the signal mostly comprised of lower frequencies? For this very reason, the concept of Fourier transform is not only important in this course, but is of paramount importance in other courses as well. Although the majority of our discussion in this topic was for the aperiodic signals. However, the Fourier transform also works for periodic signals, where the Fourier series coefficients are proportional to the Fourier transform of the periodic signal over one period. This topic will be further discussed in detail in the next lecture. So in our discussion about the Fourier transform, we have put a lot of emphasis on the representation of aperiodic signals by the complex exponentials. But why this is so important, or even representing the aperiodic signals by these complex exponentials motivated us to develop the Fourier transform representation. So the question that we'll take on here is why it is very important to represent the signals in the form of complex exponentials. And when I'm talking about the form of complex exponentials, I'm talking about either its linear summation or the integration. Before answering this question, let's have a brief recap for the periodic signals. Suppose there is a periodic complex exponential signal which is subjected to an LTI system having a frequency response of h omega. So as we have learned in chapter 3, the same complex exponential will turn out in the output as well. However, it will have some sort of scaling which is defined by this system's frequency response at this particular frequency. And since the system is linear time invariant, if the input is multiplied by a coefficient ak, the output also will be multiplied by the same coefficient. So mathematically, if we look at the input and its relation to the LTI system, we can see that the complex exponential function is actually an eigenfunction of the LTI system, or any LTI system in general, because when the complex exponential is subjected as an input to an LTI system, the same exponential function with the same frequency becomes the output. However, it is scaled by some eigenvalue, which is the frequency response of the LTI system. Now, instead of this complex exponential signal, if we have a real signal which is cos omega naught t as the input to this LTI system, what happens? From the Euler's identity, we know that the cos omega naught t can be represented by 1 over 2 exponential of j omega naught t plus exponential of minus j omega naught t, or cos omega naught t equals 1 over 2 exponential of j omega naught t plus 1 over 2 exponential of minus j omega naught t. Essentially, again we have the complex exponentials and we can use the same analogy discussed above. So the cos omega naught t here is represented by the complex exponentials, and these complex exponentials are subjected to the LTI system. Each of these complex exponential will be the eigenfunction of LTI system. The complex exponentials, being the eigenfunction of LTI system, will turn out as it is in the output. And the scaling factors 1 by 2 for plus omega naught and 1 by 2 for minus omega naught will also be maintained. The scaling factor, however, for plus omega naught will be h of j omega naught, and for minus omega naught will be h of minus j omega naught. Now suppose that the frequency response h of j omega is symmetrical. That means h of j omega naught will be equal to h of minus j omega naught. This assumption is valid for a large class of real LTI systems. But we will not go into much details about when the response is symmetric and when the responses are not symmetric. So based on our assumption, since h of j omega naught equals h of minus j omega naught, we can take this h of j omega naught term common here, and we will be left with 1 over 2 exponential of j omega naught t plus 1 over 2 exponential of minus j omega naught t, which is actually cos omega naught t. Therefore, if we are giving the cos omega naught t or a simple sinusoidal signal as an input to an LTI system, we will get the same cos omega naught t as an output as well. However, this will be scaled by the frequency response of the LTI system at this particular frequency. And if h of j omega naught is a real number, then it's simply the amplitude scaling. However, if h of j omega naught is a complex number, then we can have amplitude scaling as well as phase shifting of this sinusoidal signal. However, the frequency of that sinusoidal signal will remain unchanged. So the representation of product signals with the complex exponentials makes a lot of sense, because the complex exponential signals are periodic also. But why we are bothering about the complex exponential representation for the aperiodic signals? And one answer to this question is we want to analyze the interaction of aperiodic signals with the LTI systems. Now suppose we have an aperiodic signal x of t, which is represented by the synthesis equation of the Fourier transform, where x of j omega is the Fourier transform of x of t. Now if the input can take this form here, we want to know what happens if this signal is subjected as an input to the LTI system, and what will be the form of the output. So using the properties of LTI system, here we have the exponentials here multiplied by x of j omega and this integral here. And again, the whole integral is multiplied by 1 over 2 pi. So this whole thing will repeat at the output, and the exponentials will also be scaled by the frequency response of the LTI system, which is h of j omega. So essentially, the same input is repeated at the output and scaled by the frequency response of the LTI system. Now if you observe here, we are representing the input signal in the form of synthesis equation, and the output signal is also in the form of synthesis equation. And if we compare this synthesis equation by the standard form, we can see that this part here, x of j omega, is the Fourier transform of x of t. So therefore, if this whole output is denoted by y of t, then x of j omega multiplied by h of j omega will be the Fourier transform of the output. In simpler words, if we know the Fourier transform of the input signal and if we know the frequency response of the LTI system, we can simply find the Fourier transform of the output by multiplying the Fourier transform of the input signal by the frequency response of the LTI system. And if we know the Fourier transform of the output, we can simply find y of t by the synthesis equation, which is 1 over 2 pi integral y of j omega exponential of j omega t d omega. Another question that we may want to address is the Fourier transform contains the word transform, and the transform means modification or change. So in Fourier transform, what sort of modification or what sort of change we are performing on the signal. So when we talk about identifying the Fourier transform of a signal, we also mean that we are applying the Fourier transform on the signal. So suppose we have a signal x of t and we want to find its Fourier transform, which is capital X of j omega. Essentially in the process we are applying the Fourier transform on x of t to make it change to x of j omega. The x of t was a function of time and the capital X of j omega is a function of frequency. So essentially we are changing our perspective from the time domain view of the signal to the frequency domain view with the application of Fourier transform. And why do we want to change our perspective? To gain even more insight for the analysis of the signal. So suppose in time domain view, we can analyze the amplitudes of the signal, we can analyze the general shape or morphology of the signal, or we can analyze some other time-based features, for instance intervals. However, in the frequency domain view, we can analyze the frequency composition of the signal. We can know which frequency bands are contributing heavily to the signal and which frequency bands are not contributing significantly to the signal. So essentially we can find the range of frequencies that are significantly contributing to the signal. Now you may ask, what is the advantage of identifying the range of frequencies? So one of the industrial examples in this regard is to eliminate the frequencies that are not significantly contributing towards a signal, and therefore we can conserve a lot of bandwidth. And finally, from looking at the frequency spectrum of the signal, we can try to judge the overall nature of the signal. For example, the signal is having lower dominant frequencies or the signal is having higher dominant frequencies, the signal is band limited, or the signal is having infinite bandwidth. As an example here, I have drawn two most important physiological signals. The first one is the respiration signal and the second one is the ECG signal. So from the first signal we can see that the signal is quite smoother and oscillates much more slowly as compared to the ECG signal shown below. And if we look these signals in the frequency domain, or if we look at the frequency spectrum of these signals, we can notice some differences here. Firstly, in the slow oscillating respiratory signal, we have lower frequencies that are contributing very heavily to the signals. Secondly, we can observe here that the significant contribution towards a signal is limited to a narrower range of frequencies. On the other hand, if we look at this ECG signal and its spectrum here, we can see that the higher frequencies are contributing heavily towards making of this signal as compared to the respiratory signal. And secondly, a wider range of frequencies are contributing towards this ECG signal as compared to the respiratory signal. When we learned about the Fourier series for periodic signals, we saw that the Fourier series does not exist for all type of periodic signals. For the best Fourier series representation of the periodic signal, the periodic signal must satisfy some conditions which were called Dirichlet conditions. Similarly, for all the aperiodic signals, Fourier transform does not exist. So in this topic, we will learn which type of aperiodic signals will have its Fourier transform. Now suppose that we know the frequency transform of x of t, and using the synthesis equation, we want to reconstruct x of t using its frequency transform. So the synthesis equation is given as 1 over 2 pi integral of the Fourier transform multiplied by exponential of j omega t t omega. And note that I have represented the reconstructed signal as x hat of t instead of x of t. So when we talk about convergence of Fourier transform, we want to know under which conditions this reconstructed signal will be equal to the original signal x of t. Similar to the case of periodic signals in Fourier series, we have Dirichlet conditions that ensure that the reconstructed signal x hat of t will be equal to the original signal for any t except at the discontinuities. These conditions state that the signal should be absolutely integrable. That means the absolute of the signal should be integrable and should give a finite value. Secondly, there should be a finite number of maximas or minimas within a finite interval. And third condition is there should be finite number of discontinuities within a finite interval, and each discontinuity must be finite. For the aperiodic signals, these three conditions must satisfy. However, for the periodic signals, the first condition can be relaxed. For example, if there is a sine wave, a periodic sine wave that runs from minus infinity to infinity, the first condition will violate. However, we shall see that the Fourier transform of that periodic signal will exist. Again, more details in this regard will be covered in the next lecture. So generally speaking, we discussed that if the signal satisfied Dirichlet conditions, then the reconstruction from Fourier transform will be equal to the original signal for any t except at discontinuities. So what about discontinuities? So similar to the Gibbs phenomena, the reconstructed signal at discontinuity will be equal to the average value of the signal at discontinuity. And the reconstructed signal will show the Gibbs phenomena as it was discussed in chapter number 3. However, we must note that the energy difference between the reconstructed signal and the original signal will be zero. Therefore, we can say that the Fourier transform converges for that particular signal. Okay, to conclude the lecture, let's summarize what we have learned here so far. So in chapter 3, we have learned about the Fourier series representation for the periodic signals, and we learned that how it is so beneficial in terms of analysis of the signals or synthesis of the signals, or even finding the response of periodic signals to the LTI systems. However, there was a big void for the aperiodic signals, which makes up a large class of signals which we encounter in the real world. So our objective was to have a representation for the aperiodic signals, and the representation should be in the form of complex exponentials, because in chapter number 3 we saw that representing the periodic signals in the form of complex exponentials yielded us so much benefits. But how do we approach this objective? Thanks to Fourier, we can approach this problem by considering the aperiodic signals as periodic signals having infinite time period. And what was our inference when we started increasing the time period for the periodic signals? We saw that the Fourier series coefficients were concentrated when the time period was increased. For example, for a rectangular pulse with less time period, the Fourier series coefficients are spaced apart. But as we increase the time period of that rectangular pulse, the Fourier series coefficients started concentrating. So what happens when the time period approaches infinity? The Fourier series coefficients become continuous, like this envelope function, however with some scaling. Then we were able to derive the Fourier transform representation for the aperiodic signals. And we saw that there were two equations that came into picture, which we call as the Fourier transform pair. The first equation was Fourier transform equation, which is given as x of j omega equals integral of x of t exponential of minus j omega t dt. We call this equation as analysis equation or the Fourier transform equation. So essentially, if we have the signal x of t and we would like to find its Fourier transform, we can simply use this equation. And then we had another equation which we called as inverse Fourier transform. So if we have a Fourier transform of the signal, through this equation we can find the actual signal x of t. And we also call this equation as synthesis equation, because if we design the Fourier transform x of j omega to our liking, we can have a time domain signal with this synthesis equation. Now the transform usually means that there is some sort of change or modification. So in Fourier transform, what sort of change we are talking about? So we are talking about the change in perspective. So from time domain signal, we are moving on to the frequency domain if we apply the Fourier transform onto this signal x of t. And we saw that by doing so, we can gain some additional insight for the analysis of the signal. While discussing the Fourier transform, we put a lot of emphasis on the aperiodic signals. But the question is, does it work for periodic signals as well? And the answer is yes. The Fourier transform also works for the periodic signals, and in fact, the Fourier series coefficients of that periodic signal are proportional to the Fourier transform of that periodic signal over one period. But will Fourier transform work for any signal? And the answer is no. Because as we saw in the Fourier series as well, the signal under consideration must obey the Dirichlet conditions. So if there is an aperiodic signal and we want to know if the Fourier transform exists for that signal, then we can check for the Dirichlet conditions. However, for the periodic signals, the first Dirichlet condition can be relaxed and still the Fourier transform for that periodic signal will exist. We will cover this point in our next lecture and we will see some supporting examples as well. So I hope now you have a basic understanding of what is Fourier transform and how it is related to the Fourier series. In the next lecture, we will have a look at numerous examples showing how the Fourier transform can be identified for a signal. And we will also see that how easy it is to find the Fourier transform of periodic signals as well. As always, thank you for listening. Take care of yourself. Allah Hafiz.